Hello friends, my name is Divya Shri Vaivi, working as Assistant Professor in the Department of ECE, SJBIT. In today's lecture, I'll be explaining about the module noise, that is module number 3 in communication theory subject. So in this module, we'll be discussing about short noise, thermal noise, white noise, noise equivalent bandwidth. In the next videos, I'll be discussing about the noise in the analog modulation techniques. So first we need to understand what is noise. So noise, it is actually an unwanted wave that tend to disturb the transmission and processing of signals in communication system, and over which we have incomplete control. Actually, in practice, we find that there are many potential sources of noise in a communication system. The sources of noise may be external to the system, say for example, atmospheric noise, galactic noise, man-made noise, or it may be internal to the system. So, internal to the system, in the sense, the second category, it involves a important type of noise that arises from the spontaneous fluctuation of current or voltage in electrical circuits. This type of noise represents a basic limitation on the transmission or detection of signals in communication system involving the use of electronic devices. So the two most common examples of spontaneous fluctuations in electrical circuits, they are the short noise and the thermal noise. So first we'll take up the short noise. Short noise, basically it arises in electronic devices such as diodes and transistors because of the discrete nature of current flow in these devices. Say for example, if you take a photodetector circuit, here a current pulse is generated every time an electron is emitted by the cathode due to the incident of light from a source of constant intensity. These electrons are naturally emitted at random times denoted by tau k, where k can have a value between minus infinity to plus infinity. It is assumed that the random emissions of electrons have been going on for a very long time. So the total current flowing through the photodetector may be modeled as an infinite sum of current pulses as it is shown in the equation. X of t is equal to summation k is from minus infinity to plus infinity h of t minus tau k. So where h of t minus tau k, whatever you are seeing in the equation, it is the current pulse generated at the time tau k. The process x of t, it is given by that equation, and it is a stationary process. We call that as a short noise. So the number of electrons n of t, which is emitted in the time interval 0, t, constitutes a discrete stochastic process, the value of which it increases by 1 each time an electron is emitted. So we can have a graph of n of t with respect to t, and the mean value of the number of electrons, let it be v, emitted between the time intervals t and t naught. So the equation is given by E of v is equal to lambda times of t naught. Lambda, it is a constant and it is called as the rate of the process. So the total number of electrons emitted between the interval t and t plus t naught is given by v is equal to n of t plus t naught minus n of t. So this actually follows a Poisson's distribution, and we can have a mean of x of t, and you can have a sample function of a Poisson's counting process. So let us move on to the next noise, that is the thermal noise. Thermal noise is actually the name given to the electrical noise arising from the random motion of electrons in a conductor. The mean square value of the thermal noise voltage, let us take it as VTN, appearing across the terminals of a resistor measured in a bandwidth of say delta F Hertz. For all the practical purpose, we can express it as E of V Tn square is equal to 4 k T R into delta F whole square, where k is the Boltzmann constant and it is equal to 1.38 into 10 to the power of minus 23 joules per degree Kelvin. T is the absolute temperature in degree Kelvin, and R is the resistance in ohms. So we may thus model a noisy resistor by the Thevenin's equivalent circuit and Norton's circuit. In Thevenin's equivalent circuit, it consists of a noise voltage generator of mean square V Tn square, which is in series with the noiseless resistor, as you can see in the diagram. Alternately, we can also use Norton's equivalent consisting of a noise current generator which is connected in parallel with the noiseless conductance G. So the mean square value of the noise current generator is given by, the equation is on the screen, E of Tn square is equal to 1 over R square into E of V Tn square, which is equal to 4 k T G delta F amp square. So what is G? G is 1 over R, that is the conductance. You can also notice that the number of electrons in a resistor is very large, and their random motion inside the resistance is statistically independent of each other. So the central limit theorem indicates that thermal noise is Gaussian distributed with zero mean. Noise calculation always involves the transfer of power, how much power is transferred. So we find that the use of maximum power transfer theorem is applicable to such calculations. This theorem, it states that maximum power possible, it is transmitted from a source of internal resistance R to a load resistance RL when RL is equal to R. Under this matched condition, the power produced by the source is divided equally between the internal resistance of the source and the load resistance, and the power delivered to the load, it is referred to as available power. Applying the maximum power transfer theorem to the Thevenin's equivalent and Norton equivalent, we find that a noisy resistor produces an available noise power which is equal to kT into delta F watts. Next type of noise is white noise. So here in white noise, the noise analysis of communication system, it is based on idealized form of noise, we call that as a white noise. the power spectral density of which is independent of the operating frequency. The the name white, it is used in the sense that the white light contains equal amount of all frequencies within the visible band of electromagnetic radiations. So we express the power spectral density of the white noise with the sample function denoted by W of t as SW of f is equal to N naught by 2. Also you can see in the diagram the power spectral density of SW of f. The dimensions of N naught are in watts per hertz. N naught is usually referenced to the input stage of the receiver of a communication system. So N naught is represented as K into TE, whereas K is the Boltzmann constant. We know the value 1.38 into 10 power minus 23 joules per degree Kelvin. TE is the equivalent noise temperature of the receiver. The equivalent noise temperature of a system, it is defined as the temperature at which a noisy resistor has to be maintained such that by connecting the resistor to the input of a noiseless version of the system, it produces the same available noise power at the output of the system as that produced by the sources of noise in the actual system. So the important feature of the equivalent noise temperature is that it depends only on the parameters of the system. Since the autocorrelation, it is the inverse Fourier transform of the power spectral density. It follows that for white noise, Rw of tau is equal to N naught by 2 into delta of tau. So you can see the autocorrelation function diagram characteristics. So that means that autocorrelation function of white noise consists of a delta function which is weighted by the factor N naught by 2, and it is occurring at tau is equal to 0, as you can see in the diagram. So we note that Rw of tau is 0 for tau not equal to 0. So accordingly, two different samples of white noise, no matter how closely they are together in time, they are taken, but they are uncorrelated. If the white noise W of t is also Gaussian, then the two samples are statistically independent. In a sense, white Gaussian noise represents the ultimate in randomness. So this is what we need to understand about the white noise. Next, we'll move on to noise equivalent bandwidth. So noise equivalent bandwidth. So here we observe that when a source of white noise of 0 mean and the power spectral density of N naught by 2 is connected across the input of an ideal low pass filter of bandwidth B and pass band amplitude response of 1, the average output noise power is equal to N naught into B. We also observe that when the noise source is connected to the input of the simple RC circuit, RC low pass filter, the corresponding value of the output, average output noise power, it is equal to N naught divided by 4RC. For this filter, the half power, or you can say 3 dB bandwidth it is equal to 1 divided by 2 pi RC. So here again we find that the average output noise power of the filter, it is proportional to the bandwidth. We may generalize the statements to include all kinds of low pass filters by defining a noise equivalent bandwidth. Suppose that we have a source of white noise of 0 mean and power spectral density of N0 by 2 connected to the input of an arbitrarily low pass filter of transfer function h of f. The resulting average output noise power is given with this equation. N out is equal to N0 by 2, having the limits integration between minus infinity to plus infinity h of f square into df. And it is equal to N0, we are removing the lower limits, we are starting the lower limit from 0. So 0 to infinity h of f square into df. Next equation. So next consider the same source of white noise connected to the input of an ideal low pass filter of 0 frequency h of 0 with the bandwidth b. In that case, N out is equal to ideal low pass filter, it is equal to N0 into BH square of 0. So comparing these two equations, the average output noise power, it is equivalent to noise equivalent bandwidth as B is equal to integral between 0 to infinity h of f square into df divided by h square of 0. So thus the procedure for calculating the noise equivalent bandwidth, it consists of replacing the arbitrary low pass filter of transfer function h of f by an equivalent ideal low pass filter of 0 frequency response h of 0 and of bandwidth b. So we can also see that in the spectrum illustrating the definition of noise equivalent bandwidth. So this is about the noise equivalent bandwidth. Next we will see, we'll just brief out the noise in analog communication. So we'll have a noisy receiver model. So here what we are doing is noise gets added up only in the channel. So we need to model what is the figure of merit, what is the signal to noise ratio. Then we need to compare the figure of merit of each different analog modulation techniques. So what we will be doing is, we will first understand what is the noisy receiver model. Then we will take up each type of system like analog modulation system, amplitude modulation system, DSBSC modulation system, then FM modulation system. So according to the syllabus, we have these three modulation techniques to which we need to find the figure of merit. So we will take up this in the next video. So let me summarize what we have covered in today's lecture. We have started with the basic introduction about the noise. Noise is an unwanted quantity, unwanted waves to which we don't have any control, and depending on its characteristics we can have it as internal noise and external noise. So according to the syllabus, we have short noise, thermal noise, white noise. These are the three noises you have to be aware of. So each noise has its own quality, its own applications. Then we understood what do we mean by noise equivalent bandwidth for both arbitrary low pass filter and for both ideal low pass filter. When compared these two equations with each other, we can find out what is the bandwidth of the, or you can say noise equivalent bandwidth. So this much we have covered in this video. In the coming video, we will be speaking about the figure of merits of different modulation techniques. Thank you.